Yeah.
So after the lunch break, we have Alex continuing his lecture on massive amplitudes and black holes.
Hello again. I would like to start with actually giving some references for my lectures. So I forgot to do that at the beginning of the previous lecture. So most of what I will be talking about and have been talking about are, well, it's contained to some extent in, it doesn't? Oh, this big one? It says on? Oh, it says no low battery.
Ah, I had put it in the, okay, but now I think this was the problem. Yeah.
Oh, okay. Great. So this was the paper when the massive spinor helicity was introduced by Arkani Hamed, Huang, and another Huang, who, and some papers where I was on that contain some bits and pieces of what I want to cover. And okay. Now, regarding my previous lecture, maybe it's good if I first ask if there are any questions that somebody can remember from yesterday. Well, something that I think that maybe I didn't spell out explicitly was that in the little group discussion, I said that let's define the spinors as some matrix. Oh, I was writing it this way, I think. Some matrix corresponding to a zeta, a spinor only for one momentum, which I defined to be this. So the only reason why I defined it to be this was to have a very similar discussion for the massless case, but of course in the massive case you can also just define it to be in the rest frame. And in the rest frame you can do whatever you want here, and this is the SO3 little group rotation part. Good. So yeah, this is S of P, sigma of P psi. I think that was the notation I was using. So I was so the discussion contained that definition, but the actual but the discussion was just to justify what the meaning of these indices. So the if you have a momentum here, in the massive case, you factor it out like this. And my discussion was about the redundancy that it corresponds to this factorization. Just in the same way as in the massless case, this redundancy is by default just without the indices. It's just phase here and phase here. You can do it here just because it's factorized, but here, since there are indices, there's more, and that was the discussion about the little group. But the actual parameterizations that you use for these spinors can be anything. It can be what I referred to in the appendix of my paper, just like an implementation-wise. But you can always, you have this freedom to turn these labels with SU2. So in case somebody was thinking that I really use this as a definition for everything that I do, I don't.
Are we fixing dimension before?
The,
Are we fixing the space-time dimension before?
yes, yes. Good. So that's some remark. Well, another general remark is that I'm trying to explain how this formalism is really not something that contradicts standard QFT. It's really, and the standard QFT knowledge that you have can actually benefit from this extra formalism. So to stress that even more, let me maybe write some formulae for fields, which I didn't write before. So for spin 1/2 free field, if you quantize it, you know how to do it. So here, yes, I think yesterday I made a sign mistake, so I'm trying to fix it now. So this is the annihilation operator for spin A. Plus. Now here, it's more consistent to write it in this way. B cross A, B dagger. Of course, it's a non-shell expression here. So the point here is that just that when you consider complex conjugation or Hermitian conjugation in the operator space, you're supposed to raise this index or lower it when you apply this conjugation. And therefore, and you understand, of course, that this is minus that. So yeah, so that's a correction, but also a pretext for me to write more formulas like this that you can feed into the usual quantum field theory framework. So if you have this quantization procedure, of course, for the Dirac spinner, you also have to specify how creation and annihilation operators commute. Well, the anti-commute in the spinorial case, and the anti-commute with these standard formulae. It's just now you can really write them in a SU2 covariant way. And the same for B. The same for B. Then, yeah, and also for the Majorana case, you just say that B is actually A. Yeah. And then the same formula works. Then for spin 1, a vector field, if you quantize it, we're just doing linear theory at the moment, just the foundations of QFT. You write it in this way. So this is A, P mu, A and B, B, P. Now P mu A B. Again, when I conjugate, I raise these indices here and lower the indices corresponding to the wave functions. And so this was, the way I wrote it, this is a complex vector, but real vector, you just say, that again, that B equals A. Well, in the operator sense, not the indices. Very good. So, and the way I defined my polarization tensors for something of higher spin, for some high spin field, you would just have to do the same. It's really writing the same formula. Just lower all indices here. It's still a tensor. And something like that would be a natural quantization for some tensor field with S indices. All of them are symmetrized to be irreducible. So this would spin S integer. Good. And these guys, I did define yesterday, but let me remind you. A1, A2S. This is and all of these are symmetrized. Any questions about that? Let me then. So now I would like to. By the end of these lectures, I want to do some classical spinning black holes and things like that that are in the title. But at the moment, I've been talking about quantum field theories. I want to give more meaning to the quantity of spin, the way I defined it. So far, I haven't really defined it. I just claimed that taking 2s little group indices and symmetrizing them gives you a correct number of degrees of freedom. That's all I said so far. I just said that 1, 1, 1, 1, 1, 1, 2, and so on. That's 2s plus 1. Is that really, is that all that you want from something to be a correct quantity for spinning, to describe spinning degrees of freedom? So of course not. So I want to give more background on what happens with spin. And well, spin in quantum field theory, we need to introduce spin with respect to the Lorentz group, the generators of the Lorentz group. So the generators of the Lorentz group are natural operators to start from to discuss spin. And since I've already been doing something for spin 1 or vector, the generators of the Lorentz group in the vector representation are very simple. So mu nu are the indices for the spin for the spin tensor, but as an operator, it acts on vectors, so it has to have some other indices, sigma tau. And it's written like that. Mu sigma. And you can immediately check that it satisfies the right commutation relation. So what are those? Rho, nu, now the rho minus great. And using these generators, one can construct some Lorentz transformation, and the Lorentz transformation will just be an exponent. It will be an exponent of I, well, it's over tau, over 2 theta mu nu sigma nu. We call these sigma tau, sigma tau. So that's the way you just act on any vector, or a tensor would just rotate every component in this way. Great. So of course, I've been dealing with spinors now, and the spinors have very similar quantities. So the left-handed spinors have these quantities that do the job for them. Oh no, it's the opposite, sorry. I want to contract them this way. And the right-handed are just very similar. You can check that they satisfy just the same commutation relations, and now you can construct the Sl2c matrices that I've been talking about as well. So corresponding, having the same angle matrix for the Lorentz transformation, you can just write it as an exponent of I over 2 theta mu nu sigma mu nu, and the corresponding, what I was calling sigma tilde, just be that. And I guess it's not so trivial to check, but there is a relation between that I advertised yesterday, sigma, was it bar? Bar. How? And for reference, again, maybe, will I be using, well, actually, there I wrote a Dirac field. I will use just the same letters for the edge generators, but it's just I over 4 gamma mu gamma nu. They satisfy this algebra again. They are constructed out of these. So these are 4x4 matrices now, and the corresponding Dirac transformation will just be a block for left-handed and a block for right-handed. Great. And in a similar way, so this was for spinors, for something related to spin half, but of course for integer spins, I also have to do something. But the definition is very simple. Tau 1, tau s. This is just, so we will, so this is a tensor representation for the vectors and for the for the actual Lorentz transformations. This will be a product. But since generators form an additive algebra, they sit in the exponent. So product becomes a sum. So this will be more like a direct sum. So it will be just that. It will be, you act on the first indices, and all the other indices are not transformed. Sigma s, tau s. And so on. You act on every single entry. Okay, so these are just generators for the Lorentz group. But now, since I've defined some wave functions, I can calculate some expectation values. There will be one particle expectation value, so I'm still doing a linearized theory. But I want to give, to connect the formalism to quantities that can be interpreted as classical values. And for that, yeah, maybe I erase using the advanced technology. No. At first, wait, how did I do it? First, I just do that. Yeah. Let me not erase that. And all right. Okay, so let's compute some expectation values now. And let's discuss spin 1, because it will translate to spin s quite easily. So I want to define something like that. So for a particle of spin of momentum p, I want to define some expectation value of the spin operator. These being the particle states, well, I said already that this is just p, so I only need to say what the spins are, and I have the adjoint indices to account for that. And I define it to be just my vectors. So in the vector representation, the wave functions that I've introduced are just polarization vectors. They contain the indices, which are here. And this is my spin operator, sigma tau. Okay? Very good. So something that we can immediately check is that defined in this way, it is transverse. Well, for that, you just need to, if we write p mu here, we just remember what it is. It's well, it was over there, right? So it becomes p sigma delta nu tau minus eta nu sigma p tau. Okay, so here p is contracted with this polarization vector on one side. Here it's contracted with the other on the other side. So we see that this expectation value is 0. Well, that's actually a nice thing to have. It's actually a nice thing to have because if you have a classical spin, if you have some classical spin tensor, then if it satisfies that, then there's a one-to-one map between itself and this Pauli-Lubansky spin vector. So this can be translated back and forth. If this is satisfied. And in the classical literature, it's sometimes they use other ways to fix the spin degrees of freedom, but it's quite widely used. It's equations like that imposed on the spin tensor are called spin supplementary conditions in the classical literature. And this is in particular associated with some names. And actually, I forgot to copy that, so I don't remember the name. It's some Polish name with many complicated, something like that. But yeah. Well, it happens that my collaborators also like the spin supplementary conditions in the classical sense. So, well, now I just want to compute expectation values defined in this way, but this is just a remark that it's not a bad property to have right away. Great, and this is, by the way, so this quantity that I will be using, well, it's nicer to have one index instead of two, and also when we think of spin, we think of a vector rather than a tensor. So it's called Pauli-Lubansky. Pseudovector. Well, of course it's pseudo because it contains a Levi-Civita tensor. Great. And now I want to get to a proof of some statement that will take some board space. So please, so I'll have to erase all of that board. But I hope that the derivation will also help to familiarize familiarize you a little bit more with the formalism that I've introduced yesterday, but then you may have forgotten it a little bit. And I don't think the derivation is anywhere in the literature. No, stop. So this is slower than it's supposed to be. Okay, well, it's awful. I don't master it. Good, so I want to derive something that's slightly more general than what I wrote over there. So I want to derive what this thing is. Well, actually, yeah, it's the same thing. Yeah, it is the same thing, just with these indices upstairs. So, and I want to use the spin nihilistic formalism to actually have some to gain some understanding of the final result. But bear with me until I get to it, because it will take some time. But hopefully it will be instructive. So sigma alpha beta. Okay, so I used alpha and beta. I use alpha and beta for the sigma now. So whatever I'm writing here is sigma alpha beta. So I took whatever the definition for it was and lowered the indices. So this is beta tau, alpha tau, sigma, tau, CD, P. Well, yes? Oh, the starting point is just that, right? I defined, so this is the Pauli-Lubansky spin operator, defined just as I defined it for the classical value, but now I plugged in the spin operators relevant for this representation. And I leave these indices empty, so this will be interesting what happens with them. And yeah, this I associate to it some. Yeah, I want to interpret it as some classical some quantum mechanical expectation value. Quantum mechanical because it's just still one particle state. So I'm just allowed to do that. So of course, these two terms, they give the same thing because alpha and beta are already antisymmetrized. So let me rewrite it with different indices slightly. CD P tau. Now I invoke my definition for what these were. So these were PA sigma, well, sigma now, PB, symmetrized, and that was it, with an I. So there's two of them, so we get -1 over 2m, mu rho sigma tau, p rho, PA sigma sigma, P B dot, yeah, sigma tau PD. Well, nothing much has happened so far, but now I'm going to use some property of sigma matrices. It's just a numerical property, but it looks involved, but it's not that complicated. Mu nu, say alpha beta, sigma alpha. Oh, let me write it in a different way. Mu alpha lambda mu nu rho nu alpha beta rho gamma delta dot. So I have these sigma matrices here, and I've contracted them with the Levi-Civita. And nothing else is contracted that much. So it's really just this combination. So the question is, can anybody guess what it is equal to, at least up to a factor? I mean, I didn't derive. This formula that I'm writing is just a numerical formula. But maybe someone can guess what it is equal to. And the only reason why you could be able to guess something like that is just because the indices have to be, the end result should have all the same indices that are still here, and it somehow should be antisymmetric with respect to this alpha beta as a multi-index and with respect to this, and also it should be antisymmetric with lambda mu by themselves. Yeah, that's good. So you remembered that I had some sigma minus written with similar indices. That's great. So imagine that I write some sigma lambda mu, right? Good. So that guy would have indices like undotted indices. So maybe something like that, right? So these are spinor indices, these are vector indices. What should happen with this and this index? Exactly. Yeah? So this is almost the answer. Of course, this is an answer that's chiral, so let me write the same thing, but for the other guy. Sigma lambda mu bar beta delta dot. And this is the answer. All you need to check now is the factor. It's -2 here. You can check it. Well, I mean, basically, it's a numerical equation, nothing much. Great. So, by taking this part here, and this, yeah, I have to get the indices out of that equation to interpret more explicitly what happens. So let me write it like this. So there's P rho hanging around. There's PA. Oh, by the way, yeah, these were symmetrized. But let me not clutter the notation with that. So PA alpha P B beta. Oh no, this is C. Let me call it gamma. And PB beta dot and P D delta dot. Okay? Now whatever, I kind of wrote alpha beta dot here and gamma delta dot. So what's left is basically this formula. So I'm writing multiplied by -2 sigma mu rho with indices alpha gamma epsilon beta dot delta dot plus alpha gamma beta dot gamma dot. So now it becomes I. Why is there I? Did I forget an I? There was an I. From over here. So there's an I, and I forgot power of 3 here. That was just a normalization for the polarization vectors. Right. So I get minus here because, there was a minus already. No, I will get a plus. So when I contract these guys here, I will get a minus P, B, PD. So that's why I'm writing it. I write it a plus now. P rho, PA, sigma mu rho, PC. Whatever. There's a minus. There's an additional minus that comes from somewhere else. Great, so this was the hardest step. Now I remember what the definitions for these guys were. And also I remember that this is minus M Levi-Civita BD, and this is minus M Levi-Civita AC. So it's minus with the whole thing. Therefore, I get an additional minus on top of all of that. And now I can cancel 1 power of mass. So it's m squared downstairs. And I also, so I will write BD here, but I can also open up the definition for the sigma matrices. So they were I over 4, A, sigma mu, and then there was sigma bar nu, here rho, but it's contracted with a P. So it becomes PC. Minus P PA, P sigma bar mu PC. And very similar things happen here. AC over 4, PB, sigma mu bar, PD. Okay, so now I have momentum, the momentum matrix acting on my spinner. So this gives me P mpc square from here. From here, it gives me minus mpa square. And similarly here I get mpd here, and here I get minus m. So now from here I get angle brackets. So I can kill another factor of mass, and I by I gives me 1, so it's 1 over 4m. And well, this is something nice. So PA sigma mu PB PC. I think it's not really visible if I write it over that. I'm not sure if I'm okay. Yeah, let me write it here. P B B and D. Okay, so remove that. So I've just proven that something like a one particle expectation value for the spin vector defined in this way. Is equal to, well, actually those two pieces that I wrote there, you should remember that A is symmetrized with B and C is symmetrized with D. So actually those two terms are the same, so I can just write it as 1 over 2m in just the first term. Now I've lowered these indices, so let me write it like this. And the other index is just free Kronecker, dB. And C is symmetrized with D, and A is symmetrized with B. All right, so it got simpler in the process, but I still, maybe still you don't recognize what this quantity is, and you shouldn't at this point. Just let me write maybe already that the same thing you can do, and it just uplifts to the spin S case quite trivially. So well, the trivial part is this. The slightly non-trivial part is this prefactor. Still over 2m. A sigma mu B plus VA sigma mu VB. So this is 1, 1, 1, 1. And then there are Kroneckers all over the place. So it's B2, A2, B2S, A2S. And all of the A's are symmetrized between themselves, and all of the B's are symmetrized between themselves. So this is, okay? So I've only proven in front of you explicitly this formula. This formula, the new component, the new ingredients here is this minus sign. Well, this minus sign, it is just an issue of having the norm for the polarization vector. It's supposed to be space-like, and so it's less than 0. So there, with every for all integer spins, when you flip a spin by 1, you always get an extra minus sign because of the normalization of the polarization vectors. And S, it's just it comes from the fact that to uplift from the vector representation to the tensor representation, you need to use the tensor sum of the generators, as I wrote it, but have erased by now. So it's a sum. So you have to act with the same story on one pair of indices, then on another pair, and another pair, and altogether you will act on S pairs of indices in a similar fashion. So it will accumulate to a factor of S in the tensor case. But now I want, so this was the hardest part of my lecture. Yeah, we can make a break now, and I'll interpret the results after the break, and I'll just do some erasing now. Oh, yeah, it did. Yeah. Yeah, even though it's still working, I think. Oh, it's a single battery. I thought it was like 2 together, but no. Should I wash this?
So if you want to switch it on again, you just...
Oh, okay. No worries. Switch it. So now it's off?
Now it's mute.
Okay. Good. I'm getting better with this. Well, yeah, that stuff can be there. Yep. Is that everybody? Okay. Hello? Hello again. Let's start again. So to interpret whatever I wrote there for integer spin s, let me again downgrade to spin 1/2. The same story. It's less gory, of course, in that case. So this, yeah, now I would call it sigma mu as represented with Dirac spinners. I would actually really mean this now. Alpha, beta. Well, you can do it. It's much simpler than whatever I was doing upstairs. I think it's simpler. It becomes that. On top of that, you should remember that the spinors, they are normalized by 2m. So if I write all of that like that, I will get, so it will be 1/2, will be minus, will be 1/2 of minus 1 over 2m. Okay? Upstairs, I just had 1 over 2m. Very good. So a very similar combination occurring. At the same time, this thing can be just calculated. It happens like that. So the way the Dirac spin is usually introduced in textbooks is using gamma mu gamma 5. And this derivation is almost trivial. You just remember that however I defined them was this, PB, and gamma mu with the sigma are now minus sigma mu sigma bar. Okay? And I won't be deriving that, but this is a textbook property that if you define a spin, a unit spin vector, oh wait, it's 1/2 of that. Yes. So if you define a unit spin vector, like that, so U, PA, gamma mu, gamma 5, UPA, where no sum over A. So, well, let me define it for A equal 1. Then it will be minus the same stuff defined for the opposite state. So it will always be a minus in between. And I haven't fixed the little group in any way. So I just define it to be this in my spin-Helicity notation now. But it's really the same quantity that appears in the standard treatment of Dirac spin. Okay? So now, and a property of this quantity. Okay, I defined it. I don't need to sum in anything. This quantity is always transverse and always space-like and nicely normalized. So it's really a unit length spin vector. No. So in fact, those formulas, they are even more general than I want them to be. Let's just consider what happens with now something that I really want to associate with classical spin. The classical spin expectation value for still let's do 1/2 again. For momentum P and index A, well, I will, again, no summation over A. I will take this expectation value and also have to normalize. This normalization is really just this 2m in this case. So I just have this formula now, and just by definition of this P mu, it's either 1/2 S mu or minus 1/2 S mu. So it's plus 1/2 by definition for A equals 1, and minus for A equals 2. So my little group indices are really now just spin labels, which they were from the implicitly from the very beginning. Now let's use the upper formula for spin 1 now. So now there's two indices A, B. I use that formula. So all of this is basically to normalize. By this norm, I just mean AB squared. Well, no, actually it's not squared. It's this times its conjugate. And its conjugate is with the lower indices. So this normalization is just minus 1, minus 1/2, minus 1. Great. And whatever I see upstairs, I need to set C equal to A and D equal to B and read off what I have. So if A and C, so if A equals B equals 1, the Kronecker delta will just give me 1, and the vector there will just give me SP mu. It will give me a minus SP mu because I had a minus in this definition to get my spin 1/2 right, but there's this normalization due to the polarization vector normalization. So I really get plus S mu p. For A equals B equals 2, I get minus the same unit vector. And in the middle, I will have two contributions, and they will cancel between themselves. There will be a contribution where A and C are equal to 1, and the other contribution where A and C are equal to 2. And since and due to this property of the standard Dirac Spin textbook quantity, I will get a 0 here when A is equal to 1 and B is equal to 2. So I really start seeing how spin is quantized even outside of the Dirac, the simplest Dirac case. And I challenge you to figure out the prefactors, that they all conspire in the right way. But if you define A to S a similar quantity for the spin S polarization tensors, you properly normalize them. There will be some factorials in the normalization, which will be cancelled by the factorials, partially cancelled with the factorials coming from all of this symmetrization. But what you will get there is, again, in units of this vector P, SP, I will get a ladder. Minus S SP, and the simplest case is right in front of you, actually. The one where all of the, let me get a table here. So the one where every one of them is 1, you can just read it off to be S times S mu P. And once you get a 2 into there, sometimes there will be the opposite sign popping up because of the 2 index, and you will go down the ladder all the way to the lowest to the lowest spin state. So this spin quantization, it really is right on the nose, and you can derive it just using spin helicity formalism. So if there's any question about that, yeah?
So when you are computing the spin, you always use these angle brackets?
No.
For example, you have the spin part that you
Oh, no, these are, sorry. These are not angle brackets in this spin helicity sense. Sorry. By that I meant a quantum mechanical bracket notation. Yeah, that's.
you use U for the spin part, but you use U over V. And you can also use V, T,
So at this point, my indices, my little group indices are inside the states, and the states are, well, here it's represented by the Dirac spinors. Upstairs, they were represented by polarization vectors.
Yeah, but the question is that for Dirac spinors, you have this UVA, or you have also this anti-spinor, and the fermion described by V.
Oh, V. Ah, right. Yes.
U over V.
Yes. Oh, I didn't consider V. Yeah, because it's just another state with the. It will probably have some minus popping up in front of some quantities, but it will just be quantized just the same, right? It's a wave function for the other state of the quantum field. It's another. I'm considering the one particle states now, and here I chose my my state to satisfy this. So this is my state, right? This is one particle. Relativistic quantum mechanics from, I don't know, which year.
So if you use V, you will get.
If I use V, I will get probably minus sign somewhere. Or maybe even not. Since it's normalized, actually, maybe not. Oh, it's pseudo vector. Yeah, there will probably be a minus sign popping up. Yes, and by the way, that reminds me to highlight the fact that this is a pseudo vector. So it's pseudo vector just by definition of the Pola-Lubansky, where you have a Levi-Civita. And in the spin helicity formalism, in my derivation, it was not obvious that it was a pseudo vector. But again, when you connect it to the Dirac notation, you again see that it's a pseudo vector. There's a gamma 5 looking right at you. If there wasn't a gamma 5, this would just be a momentum, which is a vector. But you just plug in a gamma 5 there, and you get the spin pseudo vector. Yeah.
We're looking to the value of this operator, for example, AB. But from what I can understand, AB is not an eigenstate of this operator, right? Because it has this delta there. So it's not a delta on all the indices. Like if I act with S mu on CD, it has overlapping scalar product with another vector that has one of the two indexes in common. So like AB, AD
Yes.
will have a non-zero
Yeah.
scalar product.
Yeah.
So there will be some state that have like a eigenstate of the spin operator, or just
Oh, you can never have the whole spin being diagonalized, right? This is again all of these operators. They satisfy the Lorentz algebra for the four spin tensors. Now they are three-dimensional parts. This is just your standard. Yeah, the three-dimensional part of this Pola-Lubansky, you can associate it to the to the spin in 3 dimensions, and then you know that you can only set one axis along which you quantize, but along other axes it won't be quantized. And this SP is actually the quantization axis, right? It's a unit vector along which you quantize. And it doesn't have to be the momentum at this point. But it can be the momentum. So nothing prevents me from setting it to be the momentum. So if I set my SP to P, then this will be really helicities. In the massive case, there won't be chiralities in any sense, but those will be helicities. Well, helicities will be quantized along the momentum. If you boost to the frame where the momentum flips its sign, then all of the helicities will flip sign. So the helicities for massive states are not Lorentz invariant. But there is still a notion of helicity. If you switch this quantization axis to be along momentum. And the freedom of rotating this quantity is the SU2 freedom here. So again, rotating these to some other P1 prime being some U, I was calling it omega. Omega 1A of PA. If I rotate this with SU2, then here, well, from this it's not obvious, I guess, but rotating this thing here as well with the same SU2 matrix will give you some spin quantization axis that's rotated somewhere. It's rotated with this. It will be rotated with SO3 because, again, I have 2 copies of SU2, so it will be, again, a double cover kind of map between whatever I do with spinners and whatever happens with the vector. So it all knows about maths does a job. Does its job quite well here. So yeah, so the helicity basis is a nice basis to use for the spinners. So if you have some spinners, you can imagine rotating them to the helicity basis. And this basis you can use for numerics. And one thing that's good about the helicity basis is that you can define it to have a nice massless limit. Because in the massless limit, you only have helicities. The next thing I want to do is discuss the massless limit of all of this formalism, and maybe connect in this way to whatever Jake has been telling you about. So yes, so a helicity basis for lambdas and for lambda tildes, I have already said that you can just use formulas provided by Arkani Hamed up to some signs that are the same as the formulas in the appendix of my paper. The good thing that happens there is, it's actually, so if your momentum, so this is just an implementation in terms of some momentum. It's a function as a function of momentum. You imagine some implementation that takes the momentum components and spits you out something that in some frame corresponds to, no, not at some frame, in any frame, in the frame for which you chose the momenta, it corresponds to the helicity basis for the spinors. And if you plug in some momentum that looks like this, so some unit vector and some of the length multiplied by the length p capital, such that this holds, then funny enough, you can just see on the nose that your spin vector will become this. At least up to a sign. 1 over m. So that's something that happens in the helicity basis. Good. So now I want to discuss the massless limit. And I'll be erasing all of the upper board. So please ask questions while I'm doing that, if you have any. Okay, no questions. So, okay, we have these momenta. Yeah, what was the question? We have the spinors defined with respect to some momenta. Now, wouldn't it be nice if in the massless limit they would behave somewhat in a somewhat sensible way? So let's decompose them in this way. So I will call it minus, and the same here. Plus. So you can just, you are allowed to rewrite a matrix in terms of two matrices of zero with a vanishing determinant. So this matrix has a vanishing determinant, this matrix has a vanishing determinant, just because it's factorized. But together, you can decompose any matrix in this way. So, but the only thing that happened here is that I have introduced some notation. And this notation is suggestive that maybe it would be nice that this quantity in the massless limit would correspond to the same, to the massless left-handed spinor. And while this would be its right-handed counterpart. And wouldn't it be nice that then therefore this guy would go to 0. Actually, let me call it 0 O of m. Well, actually, I don't have to call it O of M. I can just say that it's 0, but then I want that to happen. And by the way, the determinant of this matrix, which is M squared, oh no, the determinant of this matrix should be M. Because the determinant of this matrix should be M, and together they should be given M squared for the complete momentum. So in terms of this, let me pick the basis in the little group indices such that this will be just O1, 1, O, and these are just the same. 1, O, O1. Then the determinant will just be a massless spinor product. And at the same time, the determinant for the other guy will be this. It's also M. So if I want, in the massless limit, the lambdas to stay finite and to correspond to massless chiral spinors, then it's clear that actually the eta spinors should be O of M. All right. Now, if you write your momentum matrix using that, you will just have a nice decomposition like that. And so this momentum will actually be OMM squared. And this decomposition, it's I think it's called light cone decomposition. You can very generally do it to any massive spinor. You can just light cone decompose a massive vector into a massless vector and another massless vector. And here there's a connection. This provides connection to the old-fashioned formalism. So before 2017, there was people were still using spinor helicity to describe massive particles. You can still do it just by doing something like that. It's a non-SU2 covariant formalism because in its essence it's just using massless spinor helicity to the massive case. So that's its drawback, but people have been using that. And the references for that are as old as 86. So basically, whenever people started using spinor helicity for massless particles, you could already try using that for massive as well. And then there were some iterations in the 90s and 2000s. So this connection, I just want you to know that that's something that other people, were already calling massive spinor helicity before all of that story even arrived. And that was non-SU2 covariant, and there's a connection there. So in that paper that I wrote when I was studying, when I was trying to figure out the spinning holistic formalism myself, I had to connect it to whatever happened before. And in section 5, there's more information on that. But I don't want to talk more about that unless you make me. Oh. Yes?
It's correct to say that one asymptotic transformation can always map you like from a generic covariant formalism to one that.
Yes.
Okay. So
Yeah.
One to connect, you have to figure out what the transformation and map into
Yes.
database.
Exactly.
Map the result.
Yeah. Yeah. Or you can just say so yeah, in that place, in that paper, I have some results in the new formalism, and then something similar was computed in the old formalism, and I was figuring out how to compare the results, and I could just see a map. I could just see how I can implement my spinners using their notation, and I get the same result. Okay. And yes, indeed, it's yes. You can always do that. There's some redundancy, and this redundancy is slightly harder to realize if you were not doing it in a covariant way, as we tend to do it now. Great. So I don't know how much time do I have? Oh, good. I still have enough time to get to the so-called minimal coupling amplitudes that I already introduced last time. But let me remind you what they are. So the minimal coupling amplitudes are just written like that. So there's some helicity here. When it's positive, we want them, they're defined to behave in this way. When it's negative, so there's A and B. When it's negative, well, there can be some other coupling constant. 2s plus h3. Well, that's how they are defined, either for gauge theory or for gravity. You can use the same form, and it will turn out tomorrow that these amplitudes have something to do with Kerr black holes. Yes. Oh yeah, I just imagine that maybe it's there's an arrow. If there's an arrow, yeah, no. If that's a complex field, then I would have to distinguish between them. If it's a real field, I don't have an arrow, then yeah, there's no distinction whatsoever. But then you see there's some signs, but yeah, it's just notation. Great. So last time I also wrote a much more general formula. Yeah, let me find it. So I wrote it for spin S and spin for two spins S1 and S2 not even being equal, but let me take them to be equal now and not bother with more exotic cases. So, like, just from the from the overall from general covariant considerations, they should be there should be some ladder of terms that behave like that. 2s minus r h. Well, you have that in your notes for the other case. 2s minus r. Well, as a whole, R. Yeah, that's nothing else. Good. And by using 3-point identities, kinematically, you can take, whenever you have some square bracket, you can decompose it in the angle bracket sense. So, well, this amplitude is just one term out of this whole thing. But this amplitude, if you rewrite it in the angle bracket basis, it will have all of them, but all of the g's here will be the same, up to some factorials and signs. But they will all be pegged to this g0. So that's the difference. So there's much less, there's only one coefficient here. The coupling constant is there's a single coupling constant here, and there's a 2s plus 1 coupling constant here. And the way Arkani-Hamed and Tu Hoang's saw that these are preferable was by looking at the massless limit. So this is why I want to consider the massless limit. But in the end, I will be using the tomorrow and on Friday, I will be using specifically these amplitudes also for black hole applications for reasons that we understand partially. Yes. Oh. Huh? Oh, I should be ending soon. Well, I've only set up the whole massless limit issue. Okay, let me derive something that will be relevant for that. So funny enough, in the massless limit, there are two branches. There's usually actually two branches in the massive case that in the massless limit map to those massless. So one of them is called MHV bar, where lambda 1 is proportional to lambda 2, lambda 3. Now these are massless spinors now. And MHV, well, lambda 1 tilde is proportional to lambda 3. And so whenever this happens, there's a way to write expressions regularly using square brackets. And here, angle brackets. And something that I want to look at is just mx3. Very simple. The definition was that it was the spinor product. Now this M was defined to be massive, but in the massless case, of course, it will just factor into something like that. Well, it was gauge invariant in the massive case. We just didn't know how to write it in a gauge invariant way. Now we can very easily. We just multiply it by 2,1 and divide by 2,1. Then this bit with this bit is unified into 2,1q, where 1 by conservation is -2 - 3. Now that 2 is massless, This is no longer an issue. So we get a 3q, which cancels with this q, with this 3q. And so what it would be get, what's the sign here? 3, 1, 1, 2, no, 2, 3. Yes, 2, 3, 1, 2. And in the same way, if you take this, oh no, I just wrote the same thing. Then it will go to 3, 1, 2, 3, 1, 2. And of course, this is a regular expression, a sensible expression on the MHV branch. No, MHV bar branch. And this is a regular expression on an MHV branch. Also, it's fine. It vanishes on the MHV branch. It's non-zero on the MHV bar because it's written in the square bracket basis. But when the square brackets are all 0, then it's regular and goes to 0. So what's important here is that there's a NAM here. It tells us that x3 behaves as O of m on MHV kinematics and as O of 1 over m on MHV bar kinematics. So let me stop here.
I've been asked to tell you how to get to the restaurant. I have not these little directions, which I have emailed to you, but you can come and get some from me during the coffee break. I don't actually have enough for everyone, so I suggest a group and share. But I can also explain this is really, really easy. What you do is you walk to Rudauer Chaussee, which is a big road, and then you take a tram, either a number 60 or 63, and you get out at Schlossplatz Köpenick. And from there you just walk in the tram direction, and you take the first right along the, well, it probably looks like a lake, I think it's officially a river, and then it's about 500 meters all in all, and the restaurant is called Krokodil, which is German for crocodile, which is not that hard, and it takes you about 30 minutes, but you can come and collect these here. And I've also been asked to bring some more paper and notepads, which I will